Okay, so we are on YouTube, so if you have any questions, go ahead and post to the chat stream there. Otherwise, I didn't bother setting up Piazza this time because nobody ever posts to it, and most everybody's here already. So if you do have any questions, make sure that you're posting to the YouTube stream. So we left off last time talking about Prim's algorithm here, that iteratively builds a minimum spanning tree starting at one particular node and then moving out and making the best choice possible at that moment in time. The example that we did was this one, where, let me go ahead and erase all of the highlights here. And I believe that we started out at A. I forget where we started out, but it doesn't really matter because all of these minimum spanning tree algorithms will end up with an equivalent minimum spanning tree. A spanning tree that, you could have 50 different spanning trees, all of weight 39 or whatever. It doesn't matter which one you actually create, as long as it is a minimum weight. Right? In this one, I think that it is unique, but I forget. But in any case, what we did was we started out with all of these triples over here in a heap. Right? Those triples were the vertex, right? So A, B, C, etc. The weight of the predecessor vertex, where you came from, and then the frontier edge. Remember that we started out with this tree edge here, and then everything in its frontier are all the things that are connected to it. So initially, this frontier is just the neighborhood of A. And then we have all these other unseen vertices. So these are tree vertices, fringe vertices, and then unseen vertices. And as we build out and we make a greedy choice on each iteration here, we choose the one on the frontier with the minimum weight, then that increases the tree and it changes the frontier. Now the frontier is everything that is connected to anything in that tree so far. And because we're only increasing it by one each time, we're guaranteed that it's not going to induce a cycle. Okay? Ultimately, we end up with all of these over here. And because you're keeping track of all these things, you can go ahead and recreate the tree without having to redo the algorithm. For example, if we've got A here, well, we know that the predecessor vertex is nothing. Over here with D, the predecessor vertex over here is A. So we know that we took this edge right here. What about F? F, the predecessor vertex was D, and so we know that we took that edge. All you have to do is look at this vertex, and you know which edges to include. You need to include A, B, B, E. Where are those? A, B, B, E. C, E, which is right here. G, E, and I think that I got them all. Right? And there's your minimum spanning tree recreated from a run of Prim's algorithm. Okay? So let's go ahead and develop this algorithm. Remember that the underlying data structure here was a heap used to keep track of all these things. And these heap these heap elements here, remember last time, were updated. That once we expanded our frontier, we looked at all of the outgoing edges, and then we potentially updated the weight or the priority over here. So we need a priority queue or heap that will support that operation. Not just putting stuff in and getting the maximum out or the minimum out, but also find an element and change its priority. And you did this as an exercise in one of your previous assignments where you fixed Gomer's work, right? You change the priority up or you change the priority down. Right? All right, so let's go ahead and write out pseudocode. And let's see, I've got to change all my colors here. Anyway, let's go ahead and write out pseudocode for Prim's algorithm. Now the notes actually have 3 different versions of this. I'm going to give you the version that I ultimately presented to you in class here. This is a vertex-based, heap-based version. Right? So the input is going to be a weighted graph. G equals V, comma, E. And implicitly, when you say weighted graph, you mean that the edges have weights. You can talk about weighted graphs where the vertices also have weights, like stopping in a town costs you so many minutes or something like that if you wanted to model that. But that's not what we're talking about here. Our output is going to be a minimum spanning tree of G. Right? And note here that I'm saying a minimum spanning tree. Like I said before, there could be many equivalent spanning trees that are all minimum. I'm going to initialize a heap here. And this is going to be a min heap because we're going to want to be pulling the minimum out each time. And I'm going to put in a comment here that it stores triples. Stores triples. Those triples are going to be V, P, and W. This might be a little bit different from my presentation, but that's okay. And they'll be enqueued with, this is well, yeah, okay. Maybe it's not, I'm not sure. I just forget. Anyway, V is a vertex. P is its predecessor, where you came from, and I think I put it third. Yeah, I put it third over here in the presentation. Just go ahead and swipe those around if you want to. And then W is going to be its weight. That is its priority. So you will have to be careful here. If your implementation of your heap, if you want to use an implementation of a heap on this, and you've got things that have the same priority, the same weight. For example, in this graph over here, we had 2 vertices, or 2 edges, with equal weight, 7. You want to make sure that they both are supported in that heap, and that it doesn't kick one out because they have equal weights. So duplicates should be allowed. Not only that, but how do you distinguish between these two? You can break ties arbitrarily. You could say that, okay, well, we'll go ahead and, if these two are choices here, which one has a higher priority? The lexicographically least one. AB versus BE, well, AB would be the lexicographically least one. Yeah?
We have to worry about making, like not a tree, like, what do you call it, like a cycle?
All right, do we use cycle detection in prims? No, if you're going to do crucials, yes. But you already did that, right, for this homework. So if you're going to do crucials, where crucials builds it by sorting all the edges and then adding an edge as long as it doesn't induce a cycle, then yeah, but not with prims. Right? Okay, so we're going to store triples in this min heap, or in this priority queue. We're also going to be building a tree. Initially, this tree will be let me go ahead and give it a name here, because that's what I do in the notes. V sub t and E sub t. Those are the vertex tree, those are the vertices in the tree, those are the edges in the tree. And I'm going to initialize this initially to the empty set and the empty set. We're going to start out with an empty tree, no vertices, no edges. And then we're going to be adding them on each iteration. Okay? To set myself up here, I'm going to enqueue a starting point. And you can have an arbitrary starting point. It really doesn't matter. I'm just going to go ahead and choose the first vertex. Its predecessor is nil, and its weight is going to be 0. Right? That's what I'm going to enqueue there. That triple right there. Again, you can start at any vertex. It really doesn't matter. The predecessor, how did you get to that vertex? Well, you just started, so there's no value there. And what's its weight? Well, if you start at one vertex, then its weight is 0. Otherwise, what I'm going to do is I'm going to enqueue everything else for all other vertices, say V2 through Vn. I'm going to enqueue them with the following triple. I'm going to enqueue, I'll say VK. I'm going to enqueue that vertex. I'm going to enqueue it with a flag value to indicate that there is no predecessor because we haven't seen it yet. And then an infinite weight. If you haven't seen the vertex yet, if it's not connected to your tree, then it's basically an infinite distance away. In this example that we just did, right, at one point, this was our tree. This was our fringe vertex set, the things that were right on the frontier. And then these are the unseen ones. They're like an infinite distance away because we haven't seen them yet. Okay? And that sets me up for the entire algorithm to start out here. Now I'm going to go into a loop. While I still have things in that, that queue, while I still have things in that heap, while I still have things over here, I'm going to move one of them over one at a time. And I'm going to do that by dequeuing the thing with the least priority and then working with it. Okay? Do I have enough room? Yeah, I think I have enough room. If not, I'll just go over to the side here. So while h is not empty, I will do the following. First of all, I need to dequeue something. So x, p, and w. This will be h.getMin. And remember that the min is determined by the weight. That's its priority. We look for the least weighted one next because we're building a minimum spanning tree. And I'm just giving these things names, x, p, and w. Okay? I'm going to update my vertex tree, or my tree vertices, I should say, to be whatever the tree vertices were before, but then I'm going to add x to this. Right? Because it's on the fringe, I'm just going to add it to my tree. I've chosen one to add to the tree. How did I get there? That will be the same edge set as before, unioned with, well, x, you got to connect it somehow. How do you connect it? That's why you're keeping track of this predecessor right here. So that is one edge, and you add that edge. That was like me over here drawing these in green. That we add this vertex here to the tree set. How did we get there? Well, f, where is f over here? F, you got there from D. So you take f and d, and you add that to your tree vertices, or tree edge set. Okay? Now I have run out of room, so I will go ... and continue over here, ... And all I need to do now is update the priorities in the queue, in the heap. Right? So for each y in the neighborhood of v, or not v, x, it should be x. Okay, I do have that correctly in the notes. V sub x. I will update the priority in my heap here. Update. I will update y, comma x, comma weight of x, y. Right? So let's annotate that with some notes here. No, I'll go with green here. Right? Actually, let me finish out the pseudocode, and that's it, and then output t. Right? Now I'll annotate this. Right? How am I updating this? That you can get to y from x. Right? So let's visualize that over here again with this. At some point I had f here. F joined my my tree vertices, and so I'm looking at its entire neighborhood here. Now this one has already been thrown out of the priority queue, so you would end up updating by finding, oh, D's no longer in there, so you're done. Ignore it. But otherwise, you might have seen these two new vertices over here. This one may have already been in the priority queue, and so all you'd have to do is update it with respect to 8. Right? But you could already get there with a weight of 7, so updating this to 8 doesn't improve the priority. Right? In fact, I shouldn't call this update at all, should I? I should call this, what's a better name? Decrease priority. Right? There we go. If the weight of going from x to y is less. Okay? That means that you can, potentially what happens to one of these things is, say, f to g over here, say this one. You saw it and you could get there by a weight of 11, Eventually, you found a better way of getting there with a weight of 9. So at some point, this said 11 over here in the heap. But then you found a better way of doing it, and so you got it updated to 9. Now, necessarily, that probably will change its position in the heap, right? If you take 55 and you decrease its priority down to 2, where does it belong? It belongs higher up in the heap. And how did you fix that? Well, you already did that as part of your exercises. All you did was you had to find it first, and then once you updated its priority, you had to go up or down depending on, you know, its relative position. If I updated this to 155, obviously I would need to swap it with the lesser of these two children. Okay. Yeah.
Wait. Would you be referring to like when we were correcting Gomer's thing?
Yeah.
On that exercise? Okay.
Yep.
Because like in the program, didn't you recommend like just using heapify?
Well, that's what I'm recommending in practice, yes. But we're talking about this from an algorithmic theoretical perspective. All right. What is so? I mean, let's discuss that. In fact, I prepared it for. Let's go ahead and just jump ahead here. Over the weekend, I did again. This is the difference between just getting it done, which I recommend that you do, versus you know, showing off and showing off your street cred and building an optimal priority queue instead of using heap queue, right? And it looks something like this. So in order to be able to change the priority of an arbitrary node here, you have to have access to that node to begin with. Because if you don't have access to it, you're storing everything into a list, meaning that you end up having to do a linear search or a BFS in order to find the node that you need to change the and update the priority on. Right? So what you have to do is keep track of that, and that's something that heap queue, the default heap implementation in Python, doesn't do. You need to keep track of the index of each item. I'm doing that with a dictionary that provides us with a amortized constant time access to that data, to that piece of data. We keep track of all of the items, but we also keep track of a map that says this item is at index I, for whatever I it is. That means that we have to do our own bookkeeping. Every time, for example, that we in-queue something, right, with a certain priority, we go ahead and add it to our list, and then we need to make sure that we put it at the end, and then we heapify it up if necessary. But as we're heapifying, we also need to update this map. This item will now map to the current index. And I have to do that when I dequeue something, and it becomes a lot more complicated than just putting stuff in and taking stuff out. When you update your priority, you have to find the item. If it's not in there, then you immediately return. But otherwise, you get the item's index through this dictionary. Once you've got the index, then it's all pretty straightforward. You either heapify it up or you heapify it down, depending on whether or not this new priority is less or greater than the old priority. I just did that with the same exact code as the enqueuing process and the same exact code here as the dequeuing process. Heapifying up, heapifying down. And I set up some straightforward, rigorous testing here. All I did was put stuff in with random priorities. I made sure that I changed the priorities to some random value here for 3 elements. Actually, I did that several times. I do it for all the elements. I just did 26 A through Z here. And then I updated all their priorities once, twice, thrice. And if I dequeue everything, I should expect it to be in order. So 333 and 99. Note here that I am supporting things with duplicate priorities, right? Because you need to do that. But otherwise, there's an implementation of a priority queue with support for updating the priorities, either up or down. Yeah?
So this would be like the showing off method, and you recommended just getting it done when it comes to updating the weight? Or
I mean, I would recommend your first iteration to just use heap queue, right? And then once you've done that, then go back and, you know, play around when you've got time for your own edification and for your own learning. Go ahead and go back and make a priority queue that supports this additional operation. Okay? Let's talk about a little bit about efficiency. So, first of all, is this big enough here? How expensive is it to update a priority, or updating the priority of a single element in a heap will be at most what? Order what? So first of all, what are we storing in the heap? A triple, right? Which is a vertex, its predecessor vertex, and then the weight. Right? So at most, how many things are we storing in that priority queue?
3 times
Well, okay, just treat the triple as one thing. So how many triples are you storing in that heap? At most.
the number of
Well, how many did we store here? At most. 1, 2, 3, 4, 5, 6, 7. Why? Well, in the pseudocode here, we do put in that first one, right? We do put in that first vertex. And then all the other n minus 1 vertices, we put those in. So in the beginning, we have at most n, right? So I'll observe here. Observe. We store triples of vertices. So at most n elements are stored in the heap. Updating the priority of a single element in the heap is at most what? The depth of the heap. And if there are n things in the heap, what's the depth of a full tree? Log n. Right? Right? But, of course, again, another observation, the size of the heap decreases with each iteration, but that doesn't matter. Each iteration, how many do we do? Number of iterations. So how many times we store log n things in there? We take one out on each iteration. So how many iterations are there actually going to be? N, right? But not only are we pulling stuff out, right? Get min means we do order log n get min calls, but n times. So this is, from this perspective, putting stuff in, taking stuff out in total is order n log n. Right? There's probably a better, easier way to state that, but hopefully you get my meaning there. Again, let's go back to the pseudocode here. Here's the main while loop. How many times does this while loop execute? Well, if you have n things in that heap, it executes n times. So this operation, if this ends up being your elementary operation, this is executed n times. What's the complexity of this one operation? Log n. So in total, with respect to this loop and get min, that's going to be n log n. It's kind of like a heap sort. In fact, it is exactly heap sort. You put stuff in, and then you take it out. You put it in once, you take it out once, and that's it. Yeah?
what about like the update?
Exactly. So, also, we do priority updates. Right? If done with an efficient heap implementation with free access to heap nodes, right? And by free, what do I mean? That random access that I implemented over here, right? That I'm keeping track of all the indices using a map. The map gives me amortized constant time updates, so that if I've got, I want to know where element say P is stored, it tells me, oh, it's at index 5, right? It's not at index 29, that's its priority, that's different, okay? But it tells, this map will tell me that it's at index 5. That's essentially free. And if you can do that for free, then once you've found it, there's no cost to that. How much does it cost to update its priority? How much does it cost to heapify it up or heapify it down if the priority has been changed? Each update, oh, well, finding the node is constant, but updating its priority is what? Order log n, right? Again, why? Because if you have it way down at the bottom and it needs to be heapified up, it's going to be with respect to the depth. The depth is always logarithmic. If you change the priority at the root node and it needs to be heapified all the way down, again, it's at most log n. That's why I say big O of log n. It could be that updating this priority means that you don't go anywhere. For example, over here, if I updated 55 to 56, would that change its position? No. So you could get lucky and not have to heapify up or down. By the way, you'll only do one or the other, right? Because if the priority increases, that means it's going to go up, not down. And if you're going to go down, you're not going to go up. Right? So it's actually quite efficient to do this, but how many times do you end up doing it? Right? So how many total update priority operations do we do? So again, let's look at the pseudocode. We call this update operation once for every vertex in the neighborhood of this vertex. This is nested within the outer loop, which is executed for each vertex. So for each vertex in its neighborhood, we update the priority. What does that tell you about how many times we execute this one operation right here? It could be n squared. Certainly that's an upper bound, but more accurately, the number of edges, exactly. Why the number of edges? Because you've got x here, and then you're doing it for each y in the neighborhood. Well, what constitutes the neighborhood? If you've got x and y, there's an edge, right? If that edge is not there, it would not even be in the neighborhood, and you wouldn't even consider it. So we end up doing this, we actually end up doing this twice. 2 times m, where m is the number of edges, because we do it once when x, with respect to from x going to y, and then we do it again when we've got y going to x. Right? So we end up, kind of like the handshake lemma, right? You need 2 endpoints in order to make a connection. We do it once from this direction, once from that direction. But it doesn't matter because 2 times m, 2 goes away with big O analysis, and we can say that we do, how many times do we update the priority? At most 2m, right? Where m, again, is the usual way of writing the number of edges. So if we consider this, the complexity with respect to update priority operations is order m times log n. Now why? Because how many do we do? M. And each one is log n, right? And so we can put these two things together and come up with what? In total, we have n log n from up here, and m log n. Right? M dominates because if m is less than n, then you have a disconnected sparse graph to begin with. Right? And so it's m log n. You can get this down to even a little bit further. I think you can get this down to m log m, but that really doesn't change the scenario. If you use something called a Fibonacci heap, which is just another heap implementation that's more complicated, but it squeezes out just a little bit more efficiency with these basic operations. Okay? All right, questions on this? No? All right. Then we're going to look at this algorithm from another perspective. This algorithm is the exact same algorithm, but when you apply it to a different problem, they call it Dijkstra's algorithm, because he observed that you could use this algorithm for something else. So given a graph G equals V comma E, directed or undirected, with weights, with edge weights, and a single source vertex, S, we want to output all the shortest distance, that is weighted distance, paths from S to all other vertices. Right? And that's what we call the single source minimum distance graph algorithm, right? Shortest distance, basically. As you saw in your last homework that you just completed on Friday, does DFS or BFS produce the single or the shortest path? Certainly not. You came up with 2 counterexamples for both of those. DFS certainly doesn't, because it goes as deep as possible, and it could have missed a shorter path over here to this other vertex. BFS doesn't work. BFS works only if you've got an unweighted graph, or a graph with uniform edge weights, where all the edges have the same weight, right? But it doesn't work when you've got, say, and the counterexample that most of you used was, say, a triangle where you've got 1, 1, and 10, right? And then BFS would end up with 1 and 10, but the shortest distance would be 1, 1, something like that. Right? Dijkstra's, however, solves this problem. If I gave you a single source, and then it would end up finding the optimal path to any other vertex in the graph from that source. You could easily run this multiple times if you wanted to find all of the shortest distances between any 2 vertices. Right? All you'd have to do is, for each vertex, right, start it there, start it there, start it there, start it there, and you found all the pairs of shortest paths. I'm going to focus on one iteration of this algorithm where we're given a single source. Okay? It is essentially the same algorithm as Prim's. You start at that source, and then you build these tree vertices, this frontier of vertices, and then these unseen vertices. In fact, you use triples, you use a heap, you use everything that's the same except for your criteria for the priority. Right? Again, we keep track of a triple. The vertex, the distance to the vertex, the shortest one that we found so far, and the predecessor of that vertex, so that we can rebuild these paths eventually. Okay? So let's go ahead and take a look at one run of this algorithm. Right? And for that, I'm going to go ahead and give you a directed graph. There we go. This is the one from the book as well. Go down a little there. This will work for undirected graphs or directed graphs. It's just a little bit more interesting if I give you an example with a directed graph. Okay? So first of all, let's go ahead and suppose that we start at A. Lexicographically. Is that going to be at all interesting? No. Can I go to A from anywhere else? No. I can get to A from a lot of places, but can I go anywhere? Nope. So let's not one run of Dijkstra's algorithm where A is your single source is done, right, at that first iteration. You'll find that everything is an infinite distance away. How can you go from A to I? You can't. So you would say that the weight is infinite. In fact, that's the placeholder value that we're going to use. Okay. I never checked to make sure that the audio was working, but maybe. Yeah, that's good. All right. All right, so let's do something more interesting here. Let's do it from E instead. Okay? Now, from E to E, let's think about that for a second. E, how can you get to E? You just stay there. So what's its predecessor? Nothing. What did it cost you, if you started at E, what did it cost you to get to E? Nothing, right? You're already there. So just like Prim's algorithm, that's how we start out, right? In fact, that's the exact same triple as Prim's algorithm. What about the rest of this stuff here? A, B, C, D, E, F, G, H, I, and J. Right? Initially, none of them are seen from anything. And they are all an infinite distance away from E. Right? Not necessarily from any other vertex, of course, because you can look at the topology of the graph and see quite clearly that it is a finite distance from a lot of things. But with respect to E, and looks like I've already screwed up, we don't need you. You're at the top. There we go. Oops. There we go. There's my heap. Right? Now on the first iteration, this is my initialization. Now on my first iteration, what am I going to do? I'm going to pull out the thing with the least weight. And this is done over here. This looks very familiar, hopefully, from Friday. This is exactly Prim's algorithm so far. Right? Now where does it differ? So that is me highlighting E here. I look at the neighborhood of E. I can go to B, I can go to D, I can go to G. By the way, can I go to H? That's not the orientation of the edge there. So I can go to B, D, and G. B, D, and G. Let's look at B first here. So far, I've found a path, an invalid path of infinite weight. If I go from E to B, I can get there at a weight of 5. Is 5 better than infinite? Yeah. So what do? We update the priority of B, as well as the predecessor here, E, and 5. Now again, the interpretation here is that you can get to B if you go to E. If you go to E first, predecessor. So if you go to E first. If you backtrack, we'll see how this works next time. But if you start backtracking from B, you go to E. You came from E at a weight of 5. Let's get a couple more iterations here to understand that. D will be updated as well as G. D and G are updated to what? The predecessor is E in both cases, because that's the one I'm currently considering. And then their weights are 5 and 15. Is that right? 20, sorry. 20, right? These 3 vertices, okay? Now I'm not coloring them in green yet because I have not taken them over to my done pile, okay? But those are the edges that produced these updates over here. Next iteration, what do? You take out the one with the least priority. There are 2 of them with 5. You can break ties arbitrarily. I'll break them lexigraphically here and take this one out. That solidifies one of these paths. That path right there. Okay? And that makes B now part of my tree. Okay? There we go. And now I look at B's neighborhood. Well, the neighborhood is what? Is only one thing. I can get to A at a cost of 7. Right? At least that's how Prim's would work. So I need to look over here at A, and you can now get there at a cost of 7. How? By going to B first, and then 7. But wait, stop. Is that really the cost of getting to A? No, what did I have to do first? I had to go from E to B in order to get to A. What is the actual cost of getting there? Not the tree cost. If we were building a minimum spanning tree, this is exactly what we would do. Oh, that's 5, that's 7. They're independent of each other, right? But they are not independent of each other now. In order to use this edge, I had to use this edge first because I was coming from E. So what is my true cost? 5 plus 7. The cost of getting there plus the cost of going to the next vertex. And so what would that be? Not 7, but 12. Okay. Let's continue. Now, what's the next one I pull out? Oops. D here. Right. That gets solidified. And, oops. Keep my colors here. Green and my highlighter green. There we go. Now I look at its neighborhood. Well, do I bother looking at B? B is already out and in the done pile. Don't bother looking at it. But I have this vertex, this vertex, this vertex, and this vertex. Interestingly, let's look at this one first, A. It cost me $5 or whatever to get to D, and it would only cost me $5 to go from D to A, the total cost being 10. Is that better or worse than what I found so far? 10 versus 12 is better. So not only do I update the priority, but I also update the predecessor. B is no longer the best route to get there. D is now the best route with a total weight of 10. Likewise, C will get updated to what? Predecessor of D, because that's what I'm going to continue working here. And instead of infinite, what is it now? 25, right? Why? $5 to get me there, another $20 to go to C, and so 25 total. Again, 5, 20. What else? F gets updated to also 25. And G. G, let's look at that. It cost me $5 to get there. It cost me $10 to go from G to D, so $15 total. And is that better or worse? Better. So D, and then it only costs me 15 now. Right. So I'm updating these priorities as I go along. What's the next thing I pull out? This one. That solidifies D. How do I know where I came from, other than the picture? I got to A. How? From D. So I know that I need to keep this edge right here. Now, am I going to end up updating anything in the heap here? That's a universal sync. There's no outgoing neighborhood. I would execute the for each loop, but then the for each loop would execute for 0 iterations, and I continue. Next one to be pulled out is this one. So I'm going to G from D. So this, and that becomes part of my tree now, basically. Although we're not building a tree, it ends up being a tree, but it ends up being a minimum distance tree, not a minimum spanning tree. Right? And I look at its neighborhood, which includes I and F, and that's it. Right? So let's consider I first, because that's the easy one. How much did it cost me to get to D? 15. Note here, I'm not going along and recomputing this. I'm storing this as part of the triple, 15. So it'll only cost me $5 more to get over there. That's 20, and that's certainly better than infinite down here. So I gets updated with a predecessor of G. Also F. You can get to F at a cost of what now? 15 to get you there, another 10, so 25. Is that better or worse or the same? Same. So break ties arbitrarily. I'll just go with the path that I've already found, not update it. Next iteration, what comes out? I. And so you have that that edge right there, and this is now part of your tree. Looking at its neighborhood here, that's only F. So what did it cost me to get there? 20. It would cost me $5 more to get over to F, 25 total, but is that any better? Nope, so stick with what you got so far. Okay. Next iteration, again, you can break ties arbitrarily. I'll go ahead and pull this out. There's nothing in the neighborhood to update that hasn't already been discovered. So C Next one I'd be pulling out is F. And what would happen then at that point? I would pull both of these out and put them over here. Still, why? Is there a way to get to either one of H or J? From E, I should say? Nope, they remain infinite. What is the shortest distance from E to H over here? It's infinite. You can't get there. So it will still find whether it'll not only find the shortest distance, but it will say, well, the shortest distance is infinite. And if it's infinite, then by implication, you know that there is no path from E to that vertex. Right? So what does the pseudocode look like, do you think? The exact same pseudocode as before, except that what? Instead of this weight over here, what do we update it to? Not the weight of the edge, but the weight of the priority so far plus the weight of the edge. Otherwise, it's exactly the same. So Prim gets credit for this version, and Dijkstra gets credit for this version, even though they're exactly the same algorithm with just different criteria. Right?
Isn't that kind of how programming languages work sometimes?
Yeah, that's how a lot of things work. Of course, Dijkstra never called it my algorithm, call it Dijkstra's algorithm, right? If I came up with something, I wouldn't call it Burke's algorithm. You need somebody else to recognize, oh, they wrote the paper, so we're going to call it Dijkstra's algorithm from now on. And then you got to make sure that you live on the same continent and you're within the same circles. Otherwise, the same concept independently developed by two different people gets called one thing on one continent and another thing on another continent, like the Church-Turing thesis. Church came up with the thesis in one statement. Turing came up with the exact same concept, but using different tools. And so it's Turing's theorem or thesis, or it's Church's thesis. Well, okay, we'll call it the Church-Turing thesis now. Yeah. All right, so questions on that so far? Otherwise, you could, I'll probably forego the pseudocode because, again, it's exactly the same. And again, exactly the same complexity as well. Right? But it only works for one source. What ultimately you want for your assignment is you would end up rerunning this n times for each vertex as a source, potentially. If you want all of the pairs, I want for any x and for any y, I want to know the one path for all of them with one algorithm. That's the algorithm that we'll go over on Wednesday. It's called here. Let me switch over to the notes here. It's as I was saying, if two people came up with it at the same time, we'll go ahead and put their names together. Floyd Varshall. Varshall's algorithm, I think, did it for the transitive closure, and then Floyd realized that it works on weighted graphs to give you the all pairs shortest path. Right? This is an all pairs shortest path algorithm. You only have to run it once. However, its complexity, as usually presented, is going to be order n cubed. Because it's going to operate on a matrix, n squared, and you're going to do this n times. So technically, it's actually n to the 1.5, so it's sub-quadratic, because your input size is n squared, but we'll get to all those details on Wednesday. All right? All right. Have a good day.